And I'm going to submit this so that we're live in feed loop. We should be live in feed loop. Let me just double check that we are, in fact. And it looks like we're all systems go. Let me see if that's coming through a feed loop, and it looks like it is. Okay. Good. Let me close this extra thing. So, welcome one, welcome all. I see we've got a slew of participants who are showing up in the Zoom directly through Feedloop. We've got some people who are on the live streamed YouTube, whichever is convenient. There's a little bit of a delay there, which makes it maybe a bit trickier to ask questions, or you have to ask questions and we'll have to wait a little bit to give a response. So it's an enormous pleasure for me to have Hae-Won Park, for him to make the time. This is an awful time zone if you're in Seoul, Korea, but he's done it for us so that the other people for whom this is the most convenient time zone can have their say and can ask some questions. Now, I will say, at the end of these little videos, I put a little comment saying, please submit a question if you have anything for Q&A. We didn't get any questions submitted this time, so I may have to chalk this up to be a failed experiment. But I think that there's some people for whom this may be the only opportunity to ask or to submit something for Q&A. And so in terms of accessibility, I'll try to keep those running. But maybe my optimism that we're going to get a bunch of questions beforehand is fading a little bit. So the way we're going to run this is I'm just going to ask Hae-Won some questions, and I'm going to keep an eye on the Q&A here in Zoom. And the moment anyone has a question, I will read out the question and we'll take it from there. And absolutely, other people's questions have the priority here. I feel like over the end of RSS, all the participants will have seen far more than enough of me, and they'll be tired of me jabbering on. So first of all, let me say thank you for the talk. I really, I'm not a person who works in legged locomotion, but I was incredibly impressed, and so I was actually also quite surprised to see actually how much I thought I really understood, actually, because there's a whole section of special work that you've done, which is, I would say, of sort of a more algorithmic flavor. I'm a computer scientist, but I mean, in terms of optimization, a real part of the talk, sort of the middle third, where you were talking about model predictive control and various techniques that you used to make that work, to make that operate sufficiently quickly. And so I've got several things that I kind of wanted to ask you, but maybe I can start with a sort of a naive question, which is about gate patterns. So especially in sort of the simulation at the very end, you gave lots of examples of gate patterns and then transitions between gate patterns, very smooth transitions between gate patterns. Can you explain to me, I mean, I know what a gate is. I've been on a horse that trots versus canters, or in Texas, they say lopes, versus walks, and they feel different and so on. But what is their significance? Do they have different sort of energetics? I mean, obviously they're related to speed, but I know it's a naive question, but maybe you could just enlighten me a little bit about that.
Okay, so I think it's a great question, and I think the quadrupedal animals has more gait pattern than bipedal animal like us, because they have more legs, and you know that they have more like possibilities having more gait patterns because they have more legs. So I think they have trotting and galloping and bounding and canter, something like that, and then they tend to use some gait for certain speed, so for certain speed range. And then there's just some paper, I think it's from Nature or Science, but I don't know which one is correct. But the paper said that they choose certain gait pattern to kind of save some energy, like metabolic cost. So in animal, I think it's a very clear answer, and I think it's a very reasonable answer. But for robotics, we don't know which gate is actually more preferable for certain range of learning speed, because when I tried to make the MIT Shitatu robot run very fast, I used bounding because my former student of Sangbest lab, they made the robot run very fast with the trotting gait. So I thought that making the same gait is not fun thing to do. So I chose bounding gait. And I mean, if animal runs bounding gait at that speed, they should be very inefficient. But we found that the efficiency was not very worse than the trotting gait. So I don't know the significance in terms of efficiency in robotics, in robotic learning. I think it's partly because they use different actuation scheme to the one we have, like muscle and tendon.
Yeah.
So yeah, I mean, it just looks different. That could be significance, I think, for now. Yeah.
Yeah.
And but I don't know. I mean, but my colleague is using reinforcement learning to train the gait, and they actually didn't specify the gait pattern, and they just try to make the robot run as fast as it can. And they told me that the emerged gait was trotting, not bounding or galloping for their robot. So this is not published result. So it's not verified thoroughly yet, but it's I think it's interesting fact, yeah, for now.
Yeah, that is interesting. And are all the gate possibilities? It's like a combinatorial question, right? There's some number of gate possibilities, and then that's it. And then some of them are going to be horribly inefficient. Like, I mean, I have two legs, and so maybe I skip, or I watch. We don't pay. I didn't pay any attention to our gate until the first time I watched the Olympics, and there's this walking, and you're like, "What the heck is walking?" What? And then you realize, like, oh, this is actually fundamentally a gate without a I guess out of flight phase would be, I guess would be the term that you'd use. So, thank you. Actually, I never kind of considered that whatever the energetics are, or the metabolic cost, I guess, as the biologists would say, yeah, those conditions don't necessarily apply if you've got, these completely different hydraulic actuators or electrical actuators and so on. And so it could perfectly be that the best ones for muscles and tendons are not.
I totally agree with your idea that, I mean, there should be really bad one, there should be really good one, but I think it's very difficult to distinguish good one, really good one, best one, and because we don't know which cost we have to look at to determine decide which one is best, which one is a good one, something like that. So
yeah, and I mean, I guess there's also, there are other costs like wear and tear, for example.
That's true. Yeah.
I know someone who jumps horses, and they say that a horse has a finite. I mean, it's kind of trivial when I say it, but they say a horse has a finite number of jumps in it, and so you have to be considerate when you think about that. Which is interesting, and maybe it's a factor that you have to be very close to optimum efficiency to see the differences, right? It's like if I'm planning a path through an environment and I'm taking a pretty poor one, I can have a bunch of pretty poor ones. It's only when I get tight up against the constraints, when I'm really smashed up against the constraints, now you can really see the differences. So maybe we're not quite at that level of energy efficiency.
Not yet.
That's interesting. So one thing that I found so I'll pause here just to solicit from the audience again. If you want me to stop talking, one way to do that is to ask some questions, and we can hear some other voices. But so I'm a person who works predominantly mobile robots with wheels, right, and multi-robot systems. And so the videos that we see, we'll see, you have an IROS video or an ICRA video or RSS video, and we'll show robots doing stuff, and there'll be a little X and it will be, you know, X10, which tells you that they sped it up. And I watch your videos and I see an X6, and you're telling me that you slowed it down by a factor of 6. So there's a huge difference in kind of, I guess, what our videos need to do in order to show this. And I mean, it's a silly thing to say, but one of the things that really stands out in your talk is the range of timescales that legged locomotion is really dealing with. I mean, you said you've got this, got this controller is running at 100 hertz. You have to work very hard to get your model predictive control to run fast enough so that it's, you know, that it can bound over the obstacles. And that a few times you said that, like, oh, we got this, so 200 milliseconds, and 20 milliseconds, and that's enough for it to bound over an obstacle. So I kind of wondered about a lot of the things you showed were dynamic, and I tend to think of, I guess I tend to think about animals with 4 legs as one of the advantages is they can be statically stable, because I can imagine planting your 4 legs down, or 3 legs and pointing or whatever, and then thinking hard about where I'm going to plan my foot placement and so on. And you know, you had this great example of a guy on the climbing wall, and he's climbing without his arms behind his back there, right? But there is a motion where you can see kind of, he knows what he's doing. He's doing it controlled, but kind of slowly, and he knows he's shifting weight, and then there's a swinging portion, but there's also kind of clearly a planning phase. And so my question is sort of about the high end, the slower timescales. There's foot placement, there's sort of perception. And what's always incredible to me as someone who works in that space is that how far you can get away with the things at the lower level. Like a lot of the things you showed were without perceiving, I think, changes in the world. No perception, but it could kind of, it could stride in various ways. And we have at RSS this year, from Oregon State, there's an excellent example of an RSS paper where they've got, you know, bipedal locomotion, and they're not sensing, and it's very robust to that. But what are your thoughts about the slower timescales, or are they less important than we think they are? That's my question.
I think I mean, I think it's not very, it has not been very long time that legged robot works very well and run very fast. So far we have been focusing on making the robot run and walk as fast as it can, as stably as it can, something like that. So we've been focusing on making basically periodic motion, good periodic motion. So the tight integration, I think if I mean, long time scale planning becomes important, we need to, I think, good vision perception system, very tightly integrated with the legged system. So if that happens, then the long-term planning would be important. So for example, if you want to go upstairs, I don't think you need to plan, you need to have a really complex plan for foot placement. But if you try to jump or climb up like 50 centimeter step, then where you should put the foot would be really important things. And then you need a good vision system in order to obtain the geometry of the environment. So I think the legged robot community is actually going forward to tackle those kind of problem now, integrating vision, integrating localization with the legged robot low level control. So, I mean, as we know, Boston Dynamics achieved really good performance right now, but we don't know what's going on behind of that video yet. But the academia is also working on that kind of problem now. Yeah, and I think it's really important in order to make the legged robot more useful than now. Yeah.
Yeah, no, I can see it. I mean, your examples of the a couple of places you had these squirrels jumping around doing amazing things. Well, you had lots of examples, the bear climbing the tree, and these that I thought were really great. But the squirrels, yeah, utterly amazing, and I kind of needed to be reminded how amazing they are, because I see them wandering around, or you would see,
everywhere.
everywhere, right? See them in Michigan. and you don't pay attention to actually how really capable they are. And it's also kind of curious because some of the things they're doing, they can't be planning. I mean, there's this one case where in the video you showed, it jumps onto something and then that thing is shifting. And there's no way I could have perceived beforehand that it was going to shift, but I don't know, it seems to have this faith that whatever trouble it gets into, it can get out of. Which makes me bring up a question a little bit because, not so we don't talk about squirrels, but cats also do that, and they're famous for falling on their feet. So the question I wanted to ask you is about falling. So all of these videos, whether it's whether it's Bambi or any of the robots you showed, or Cassie or any of these ones, you got to have a well-funded research program because you got to fund the people to carry the thing to hold the robot in case it falls down. And so, how far are we from thinking about systems that are kind of more robust in that perspective? And I mean, I have seen examples of robots that can fall over and get up. But, if I think of the DARPA challenge where there were some falls and so on, what's necessary to get there? Is then maybe that's not even a priority. Maybe that's a very stupid question. Maybe that's something you have
I think it's a very very relevant question, and I think it's important for me to say that most of the falls, it's not because of lackness of robustness of controller. It's actually about hardware. So most of the falls, for example, my robot, happens when we are using Ethercat communication to communicate with the motor amplifier with the main computer, and most of it is because of disconnection in the communication. So the computer fails to send the command to the amplifiers. Yeah, and it's not because of the controller design. So I guess I think I heard that the most of falls in the famous IEEE Spectrum video, the DRC robot fall compilation video.
Yeah,
most of them is actually not. I mean, I think half of them kind of it's not from the control design. I think it's from just the communication or hardware failure. So I think Boston-X robot is really good because their hardware, integrity, and they actually put a lot of effort on making the hardware more perfect. And I'm using experimental hardware platform that built by, graduate student, and I have to watch them to screw and solder, something like that. So even though that, I think even with that, I think we have a hardware failure a lot. So I think, and after that, I think that after that we have to think about robustness of controller itself, and then I think it could be interest problem. But I want to say that the bar that the graduate student is holding up is because of a hardware failure, not the algorithm failure. Yeah.
I see. No, that's interesting because I had always kind of imagined that it was perhaps from something slipping or something, something. I mean, contact with the world is hard, right? Right? And so it's unpredictable and so highly nonlinear and so on. I mean, the thing that I find actually very interesting about your work is as I said, how much is sort of algorithmic, and so. And I use that term quite generally in the sense that, one of the things that you touched on is that there are things like, Euler angles have these singularities that we kind of all know about, and you had a very nice animation to show that. And it turns out those singularities, they matter a lot. And it seems like actually they matter a lot in a lot of the practical things you'd like to do. Actually, a lot of the practical, but somehow the more interesting things that you want to do. Right? It seems like this backflip and some of those things all involve singularities. And so then you need to figure out, okay, the appropriate way to parameterize that. And so, look, you use the exponential map to do that. And So that's kind of interesting because there's this sort of fundamental mathematical representation problem, which comes out of the fact that you want to do this very practical skill. And it seems like the sort of thing that someone should have a podcast on, to tell, high school kids, you should learn your mathematics because you needed to do a backflip. You wouldn't believe it, but you needed to do a backflip, or whatever the case is. So I found that quite interesting. I didn't. So one thing I wasn't familiar with is this idea of a retraction map. Could you say a little bit about what that is? I'm keeping an eye on the Q&A.
Okay.
I've got a few participants who've joined, but we don't have any questions. So that's something that I was sort of very personally curious about, and I thought I could probably read it up, but I'll just ask you, and you can give me the 2-minute summary.
I want to say that that's actually deeply inspired by RSS paper presented in 2015 by Forster and Luca Callone. And I looked at their mathematical equation to handle the SO3 manifold. And I actually forgot about that for like a very long time. And when I became a professor, I started to look at some of the papers that I got very good impression. And I thought that, we can utilize this to solve this problem. So I asked my student to work on the problem. But anyway, the retraction mapping is, so you know that the SOC manifold is not vector space, but we can obtain the tangent space at certain SO3 matrix. And retraction mapping is, that if you, let's say, but you can actually obtain the small SO3, which is vector space, right? So, which is actually tangent space to the SO3. But if you go onto small SO3 space, then you will be out of SO3 manifold. The retraction mapping is just to, pull that down.
Pull it back to
the SO3
big SO. Okay, I see.
And you can actually obtain gradient utilizing this concept. Yeah, because it's about how much deviate from your operating point or your desired point.
I see.
So
it's a way for you to pull the gradient from the Lie algebra back into okay, I see. Yeah. Okay, cool. Yeah, so it would have been hard for me to find that, but you answered it excellently. So that's a good case of where we need a live Q&A. And now we've got a question and it's really an excellent question. So actually, I'm really glad you asked this question, because I just delved deep. We were just asking some very technical questions, and the question here is: if we are new to robotics, what can be the best thing to explore to start during your undergraduate degree?
Oh wow, that's a very tough question, because I don't have a really good answers for that, because okay, so it depends on which degree program you are in now. It depends on, like, if you are CS, if you are in mechanical engineering. But I'm in mechanical engineering. What I can say to the student at mechanical and engineering department is focus on, study mathematics and study programming as much as you can before entering the graduate school. And try to have many experiences to work on hardware system. I think because I'm talking this assuming that the audience hearing this is ME student, because I'm from ME background. But as a ME student, you know that you will work on like fluid dynamics, thermodynamics, and solid mechanics, which is not very close to robotics, but it's useful knowledge for mechanical engineer. So I think you should put some of your time to study on some knowledge for robotics, actually, if you are ME student, because you should have a good GPA to enter a good good graduate school. But as well as you have to compete with the computer science student and electrical engineering student for the same position. So you should have kind of how can I say, comparative skills for coding and I think mathematics. So I think that's what I can say, and try to experience as much as possible for hardware system, because that could be your real how can I say strengths compared to other students who has not have that skills. So
yeah, that can really distinguish you as someone who's applying. So I'm a computer scientist. I mean, I'll just say quickly that I think that the great thing about robotics is that it's got a little bit of everything.
that's true.
So, but there can be a tendency to sample, and you need to make sure in your undergraduate degree you're also really investing time and delving deep. So by normal I mean non-roboticist CS student doesn't need to spend too much time thinking about calculus, for example. But Jacobians show up everywhere in what we do. So you got to pay attention to that linear algebra. You got to pay attention to that calculus. And all of those things, and on the perception side, of course, probabilities and that background is worth picking up, which just means you have to be a good undergrad student, but you also have to be broader, which is I think Hae-Won, what you're saying, and I'm completely agreeing with you. So that was an excellent question, and far better than any of the questions I asked. So does anyone else have a question on those lines? Or other ones? So I do have, as we talk, I get more curious about various things. So one thing that I saw is that you have, you have a video of what looks to me is an incredibly complex mechanical device, and then you have a very simple kind of, I'll use the phrase reduced order model, showing that the periodicity is acting exactly like you would expect. And you said, look this. In this case, we're talking about the MIT cheetah, and you were saying, it's good correspondence. And so that looks to me a little like sort of what is the term? There's sort of anchors and templates type approach, where you have a very simple model, a simple. The simplest model that will do, and and no simpler and no more complex. And is that sort of what's going on in those diagrams, or am I is that just a superficial similarity that mobile robot person is seeing there?
I think it's just the idea is very similar to template anchor idea. And I think that template anchor idea has been used by UPenn guys very long time. And then I think it's different to just naming between simplified model and template anchor. It's I think I should be careful to say that, but it's a similar, I think, concept to me. And then, I think it's very difficult to prove, that, if you use a simplified model, how can you prove stability or robustness that worked on the simplified model to more complex model? It's a real difficult question. Even though you are utilizing template anchor model, you cannot prove that for like general cases. So, and same for the simplified model. So
the fundamental challenge of abstraction, right? As you throw away the details, you say, no, as I said, no simpler. How do you know that it wasn't you didn't oversimplify? That's a fundamental problem. So we don't have any more questions, and we're out of time. But we have another one of these sessions. I think, is it 8 hours, 10 hours from now? I think something like this. So assuming, maybe if you're in the US, that's not a crazy time. That's a horrible time if you're in Europe. If you're watching in Australia or in Seoul, then you've just done the horrible time, and we'll meet you back at the much more pleasant time, and we can follow up and have some further questions. And you can. I will keep the form updated if there's any. I'll keep watching that form. So if you have some extra thoughts and you'd like to pose some questions, we really value them, and part of what makes the conference a conference, not just a TV channel with a bunch of streamed videos. So please do jump in and interact with us. And thank you so much, Hae-Won, and I will talk to you a little later.
Okay, thank you for having me. Yeah, see you later.
This is mine, absolutely. Thanks. Bye.